Dr. Co. This is Matthew Park. So this is our second video in our two-part video series for homework 3 on the water and air closed system. So last video we discussed the problem itself and what equations we'd use, and then a breakdown of those equations. This one we're actually going to create a code that solves this problem. So what I have here, I've already imported all of the stuff. Just kind of like a general explanation of what this does is it's going to allow us to pull in the chemical properties for each of the substances in our system. It's going to allow us to make dictionaries and give us dictionary access for our code. I have our R value assigned in there, as well as the VSC function, which you created, which is just going to make solving these equations easier. So let's just get right into it. We're going to start by pulling in our values for each of our substances in our system. So we're going to say P is equal to CHE.props, and then we need to include each substance. So our air is going to be made up of nitrogen, oxygen, and argon, and then obviously we have water at the bottom of our system. So those are all of our substances in our system. Enter. And so now we have access to all of those. So let's just go ahead and define our model. We're going to be making two models in this video. So we're going to just call this one model 1, and we're going to say C, comma R. And so what C and R do is R allows us to report some values for later use. And then C is going to be just a combination of variables. So to start off, we want to get our water, the pressure of our water. So if you remember in the equation for the pressure of the system, the partial pressure of water is, we use the Antoine equation to find. So for this, we're just going to pull it from, we're using this like P function. We're going to input the vapor pressure of our water. So we're going to say P vape, and then we need to assign, so this is the vapor pressure at some temperature, so we're just going to say C dot T. And then we need to specify which substance we want. So if we were to just leave it like this, it would pull it for all four. But we just want for water in our array, which is number 3. So now we have our water pressure. And so the next thing we need to do is we need to get our volume of vapor, which is equal to our total volume minus the volume of our water. And then next we want to write this actual pressure equation. So this is going to be R dot P, which is equal to pressure of our system, which is going to be the partial pressure of air, which if you remember was, the equation for that was the moles of air multiplied by R and T divided by the volume of vapor in our system. So we're going to do C dot air underscore N times R times C dot T underscore I so this would just be C dot T, and then that's all divided by V underscore vapor. And then finally, we just want to return pressure of our system and the pressure of our final pressure. So now we have our model, and the next thing we're going to do is we're going to use this dot map function to create kind of a dictionary. It's just going to make it easier to access all of our values. So we're going to say C equals dot map, and then we're just going to start typing in each of our values. So we're going to say C dot total is our initial value of our initial mass of water which they gave us, which is 1.0 kilograms. We're going to say C dot volume total, which they don't actually give us, but we're just going to estimate it's about 0.01 cubic meters, or 10 liters. The next is C dot P underscore I, so our initial pressure, so they give us to be 1 E to the fifth. Then our final pressure, C dot P underscore F, which is equal to 2 E to the fifth. And our initial temperature, which is C dot T underscore I, and that is 298.0 Kelvin. So now we have all of our initial conditions inputted. And if we go back up here, one more value we need is this volume of water to find the volume of vapor. We don't actually have the volume of water, but we can solve for it by using this P dot roll and then add our initial temperature. So what this is this inputs this accesses the density of water at this temperature, which is going to be 298 Kelvin. And so now we can actually define our volume of water, which is C dot VW underscore I. And that's going to be equal to the mass of water we have at the beginning. So C dot WTOT divided by this density of water at our initial temperature, which, as you can see here, is 298. So now we have our volume of water, and then the next thing we need to do is solve for our volume of vapor. So we're going to say C dot V underscore VAP is equal to the total volume minus just the volume, the initial volume of our water. And so now we have our volume of vapor. And we need this value to be able to solve for the number of moles of air in our system, which gives us the partial pressure, which is necessary to find the partial pressure of air. So we're going to say C dot air underscore N is equal to, and we discussed this equation in the last video, this is going to be equal to our initial pressure. Let me put this in parentheses. So our initial pressure multiplied by the volume of vapor, and this is going to be divided by R times our initial temperature. So now we have the moles of air calculated. And so the last thing we need is we need to kind of estimate what final temperature is going to be. So the final temperature, we can define it as C dot T, and we're just going to say we use this range function to say, we'll start by giving it a guess. We're just going to say it's 360 Kelvin. And then we need to come up with a low point of the range and a high point. So we're going to say 300 Kelvin to 600 Kelvin. We know it's not going to be below 300, and it definitely should not be above 600, because 600 is very high. So now we have a range for temperature, and finally all we need to do is use this VSC function that you created, Then we just need to do VSC dot solve. And we have an error, so I'll go back and look for this. It says right here. Okay, so I figured out what error I made. So in this pressure of the system equation, I only actually put in the partial pressure of the air. So I need to include partial pressure of water. So now we have that. And also down here, I forgot to specify that I want the density of water, which is the assign the number 3 in our array. So now this should work. Do shift enter, and then there we go. Okay. So now let's just display this using VSC.VDF, and there our final temperature is. So that's the first part of this code. The next part, we need to create another model for the total volume of our system, but in relation to the moles of air. So we're going to start by doing r.pw. Actually, we can just copy this down from up here, because we know all the same stuff. So we have our partial pressure, we have our volume of vapor, and then we have the pressure system equation, and we also, I'm just going to include, move this down here too, the number of moles of air. So now we have all that, and then the next thing we need to do is we need to do the number of moles of water in the vapor phase. We need to include that in this part. So we're going to do r.w underscore n underscore vapor is equal to our, and if you remember from the first video, we also discussed this equation. This is going to be equal to our partial pressure of water times the volume of vapor. Partial pressure of water times the volume of vapor divided by R times our final temperature. So C.T. And then the next thing we want to do is we want to add two constraints. So we're going to add a constraint for our pressure. And we're going to say the constraint is equal to pressure of our system, and then our final pressure. And this just kind of sets the parameter for the final pressure. And then we also want to set one for the number of moles of water vapor. So we're just going to say constraint. And then r.w underscore n underscore vapor. And then c.w underscore n underscore desired. So this is just going to set another parameter for the moles of water vapor, and then the desired moles, which is going to be 0.3. And finally, we just want to return these two values. So return underscore constraint, and then w underscore n underscore constraint. Shift enter. Okay. And so now we're going to create another dot map. So we're going to say C is equal to dot map, and then we want to do the same thing we did before with all of our initial conditions. So I'm just going to move all of these down. We need all of these. So now we have our initial amount of water, our estimated total volume, our initial pressure, final pressure, and our initial temperature. And then we're going to need to also include the density so we can solve for that. The volume of water. Move this down as well. And then up here we included this variable called c.w underscore end underscore vapor desired. So we just need to set this equal to what we want our final moles of water vapor to be, which is equal to 0.3. And so we're going to create another range for our temperatures. So we're going to say C dot T is equal to range, and then this is the same range as before, so 360, 100, and then 600. We need to also estimate now, we're going to create another range for our total volume. So we're going to say we're going to guess it's going to be around 100. No, we're going to use our guess from before, and we're going to say it's about 10 liters or 0.01 cubic meters, and then from 0 to 100. 0 to 100 liters. And finally, we just want to use our VSC function again. So VSC is equal to this C and then model 2. And then VSC dot solve. Enter. So let's see. I forgot to include our range. Too quick. Okay, there we go. Okay, so I figured out what I did. I forgot to include this. I was going too fast and I missed this equal sign, and then I also need to change all of the v underscore vap to have an r dot. So now this should work. Okay, so perfect. So now we can also display these values using the VSC at VF. And there we go. Now we have our final temperature and our total volume. So this concludes our homework 3 video series for the water and air closed system. Thanks, and I will see you next time.